I'll start recording. Okay, so the first thing I'm going to get started with is explaining the concept of induction, because I feel that we might be using it quite often throughout the rest of series and sequences and also the binomial theorem. So induction is basically a technique, a proof technique, and the reason I'm going over it is because that's in the first topic from the way my school is going through. So proof by induction is a process of dominoes, of starting off at some point and then continually getting and hitting off all the next ones. So let me just explain how that works. I'm going to share my screen. No, this is bad. Not this. There. So I'm sharing my screen and by the way, anyone can interject at any point with a question, or if I do something wrong, tell me. I won't be looking at the chat as often, so it'd be better if you could tell me over the voice if anything is wrong. And that's all, yeah. So the concept is that you start off with the base case, right? Your base case is your starting point, which you can easily prove by just showing, but usually by just observation. So by observation, or some sort of simple proof, like a simple proof technique that doesn't require any like major steps. So this is your base case. So you start off with your base case, and then for you should just join. We're going over induction. So you have a base case, and then after that, you're using a assumed statement. So using an assumed statement. So if this assumed statement is true, which is usually denoted by some px or like just some random function, then I don't know what that was.
Okay, just continue.
Okay. So using the assumed statement, you try and prove that everyone is correct. So what you essentially do is you prove that it's true for some n is equal to k, which is some k is any selected case, which could be any case, but we can call it k because it could be any case. That's the point. And then you show that it's true for n is equal to k plus 1. And specifically, the fact that this is true is very important. You need to use the fact that this is true in proving that this is true. And that's what induction is. It's using that the previous n equal to k case is true will show that n equal to k plus 1 is also a true case. So that's what the principle of mathematical induction is. So you show a base case, right? And then if you can show, and if assuming that every single n equals to k is going to be is going to be true, n equals to k plus 1 is also true, then you can solve then that's proven by mathematical induction. And this should make sense, because if you look at a base case, say the base case is when n is equal to 1, then that would mean that if n is equal to 1, and you've shown that if any n equals to k is true, then n equals to k plus 1 is also true. What that says is that if n equals to 1 is true, and you've shown that if that is true, then the next one is true, then n equals to 2 is true. So then you can go in the cycle again. If n equals to 2 is true, then that means n equals to k plus 1, n equals to 2 plus 1 is true, and then 3 plus 1, and then 4 plus 1, and so on. And that's how induction works. And basically this part over here is the main mathematical induction portion. And in any question, the majority of the marks are hidden inside over here, and there's only there's maybe 1 or 2 marks allocated to start over here. And then of course you have to end with a statement stating this, and that gives you another mark as well for a general question. So I'm not gonna, you know what, I don't have any examples on hand for this, but I'm sure as we go through the next series of topics, I'll be using mathematical induction at some points just to show uh, that this is true and that this works. So let's go ahead and get started with, um, if anyone wants to take a note of this, they can, but I don't know how useful this is, like really, but if you want, you can. So I'm just gonna erase it, and if anyone doesn't want me to, just tell me right now over the PC. Okay, fine. Okay, so starting with the first thing, what is a sequence? There are two types of sequences that you could have. Um, you can have arithmetic sequence, and you can have a geometric sequence. One second. Oh wait, you're saying Love Lake? Yeah, okay, that's nice, but like, it's so distracting. Okay, it's fine. Your arithmetic sequences, and you have geometric sequences. Wait, I need to. It's distracting me. You know what? Can you just finish off the annotations if this is proper? Anyways, so you have arithmetic sequences and geometric sequences. These are two types of sequences, and they're the most fundamental types of sequences that you could possibly get. The properties of the arithmetic sequence is that you have a constant difference being added to a starting term. So you have a starting term, let's call it A, and that's our starting term. Okay. And you have a constant difference D, which is called a constant difference. Oh, sorry. Difference. And the sequence looks like this. The sequence looks like A, then A plus D, then A plus D plus D, and so on. And more simple forms, A and A plus D, and then A plus 2D, and A plus 3D, and so on. That's what it looks like. So that's going to be something like the sequence of odd numbers, 1, 3, 5, 7, 9. You have a constant difference of 2 between each of them, and you have a starting term of 1, which is A. And that's what the general arithmetic sequence looks like. It always looks like this. The D doesn't necessarily need to be positive. It could be a negative value, so you could be getting smaller and smaller. That's a possibility. It could be a complex number. It could be anything, and you should be versatile, understanding that it could be anything. Just anything with a constant difference that you can identify. The starting term in IB is referred to as U1. However, I might use A interchangeably with U1, so that just informing about that. But U1 is what's in your formula booklet for the starting term. And that makes sense because the nth term for IB is called UN, which is the nth term. And if it is the nth term is UN, that means the starting term is term 1, which would indicate that U1 is the starting term. Now for the geometric sequence, you have an A, which is again your starting term. U1. And then you have R, a constant ratio this time. And the fact that it's called a ratio indicates that it's no longer a sum being added, but rather a multiplication, a ratio between sequences, not a difference between sequences. So if you have the first and the second term, you're not looking at the difference between them, you're looking at the ratio between them. What is the change that is occurring between them? And the general form of the geometric sequence is you start off with your A term, then you multiply it by the constant ratio and get AR. Then you multiply that by the constant ratio again and get AR squared and so on. So this is a geometric sequence. Again, there's simple examples. You can get the sequence of starting term 1 and constant ratio 3. You have 1 multiplied by 3, you get 3, multiplied by 3 again, you get 9, 27, 81, so on. And these are the two main different types of sequences that you're going to see. Now, there's many properties of these two different kinds of sequences that may come in handy. But before I go into the sums of these sequences, it's more important to look at why specifically I'm using this notation. So obviously I could just say arithmetic sequences look like this, geometric sequences look like this, but I'm specifically putting it into an algebraic form A plus D, A plus 2D, A plus 3D, AR squared. Now, this is very useful because if you can start visualizing sequences in terms of, not in terms of like just numerical values, but also in terms of algebraic values and variables, it's easier to start comprehending that when someone tells you that the first term is this, the third term is this, the 89th term is this, then you don't have to go and get really worried about like how you're going to be finding these terms. And that's why it's a lot easier to think about it in terms of algebra than to think about it in terms of numbers all the time. So when you think about arithmetic sequences, don't think about 1, 3, 5, 7, 9. Think about A plus D, A plus 2D, A plus 3D, and so on. And in geometric sequences, think about AR squared, and so on. Now, another important thing to just look at really quickly is trying to understand what the nth term of both of these sequences is. And specific, so for the arithmetic sequence, the nth term is basically the term where you plug in a value for n, you will get back what the nth term is. So if we look at this one, we notice that a common feature of every single term here is a. So if you're going to be using the nth term has to have an a at the start of it because every single one of these has an a. We know that there's a d as well, but then there's a constant factor in front of that d. So let's think about what that constant factor is. Over here, that constant factor is plus 0d. Over here, it's 1. Over here, it's 2. It's 3. So when n is equal to 1, that constant factor is 0. When n is equal to 2, that constant factor is 1. When n is equal to 3, that constant factor is 2, and so on. So if you notice a pattern over here, the constant factor is always 1 less than n. So then you can create a quick thing saying a plus n minus 1 times d. And this is where the general form of the arithmetic sequence comes from, which is in your data booklet. Similarly, for the geometric sequence, we can undergo a similar process where un is equal to, we know there's always an a over here, and we're multiplying by some constant r. However, again, at the exponent is changing this time instead. When n is equal to 1, the exponent is obviously r is equal to 0, r to the power is 0. N is equal to 2, it's r to the power 1. N is equal to 3, it's 2. Again, same thing. N minus 1 is the exponent over here. So these are the two forms for the different sequences right over here, and this is why they exist like so. And now to the next portion, which is trying to show, trying to prove really quickly, I mean, not really quickly, it'll take a little while, the next few things from the data booklet. So if you notice from the data booklet, we have this, we've proven this little thing over here, the nth term of geometric sequence, we've proven the nth term of geometric sequence. And the next two things which are most interesting over here is this one over here, and then this one over here. And essentially, we'll try and prove these two things are true as well. I'm putting a very strong emphasis on proofs throughout for the HL curriculum, specifically because the AHL curriculum has a paper 3, which is completely different from the Math HL paper 3. And the AHL paper 3 is a long answer question. So they're going to give you very long questions. You'll be introduced to new concepts. You'll be introduced to generally very complicated things where you need to try and make sense of it. And you will most likely need to be able to prove things, which is why the textbook puts a very strong emphasis on this. And I feel that even I should put a strong emphasis on this while I'm going through it. And for every single formula in this booklet, you should know the derivation, the proof for it. This wasn't necessary in previous curriculums, but in this curriculum, I feel that it is absolutely crucial that you know this, or that you at least know the general ideas behind what this occurs. So first of all, we're going to think about the sum up to the nth term, and then we're going to look at the sum until the nth term for geometric and sum of the nth term for arithmetic. Before I jump in to sums, I just like to make a notational point. So I think I'm just going to leave this, and I'm just going to move it down here. So. Just a quick notational point. So I'm just gonna move to red. A notation that is commonly used is sigma notation. Sigma is not a complicated function. It's a very simple function. All it does is that it's like a computer program telling you exactly what to execute. And what the sigma function does is that it has something in the front of it. So let's say for the example, for sake of example, it's 2x plus 3. And then what it does is that it takes for different values of x, it adds up all the different possible values if you have different values of x. So let's think about what that means. So if you start at x equals to 1 and go up until 10, right? So what this sigma function is saying is that you start at 1, you plug in 1 into this little function over here, the 2x plus 3. You plug in 1, whatever value you get, you start that at you append that to the start of your sum. So let's think about what that does. So 1 gets in over there, you get 2 times 1 plus 3. And then what you do is you go from 1, you go one step closer to 10. So you go to 2. And then you do the same thing for 2. You plug in 2 and you append whatever sum you're going to get from that. So you get 2 times 2 plus 3. And then you do the same thing for 3. And you keep doing the same thing until you reach 10. And that's what the sigma function does. So just going to be clear over there. The 10, it doesn't, the number on the top necessarily does not need to be finite, which means it doesn't need to be 10, 11, 12, and so on. It can also be something infinite, which is what is called a series. So when you're looking at sequences in finitely with just a set number of terms, you would look at them as series. But when you're looking at a series in sums of their entire sequence and up till infinity, then you would call it a series. And the sigma function lends its way to that. Okay, so the next, so let me go to the sigma notation. We're going to go to the proof of the arithmetic progression. So, is this infinitely large? Oh no, it's not infinitely large. It's that. Why can't I move anymore? That's weird. That's annoying. Okay, no, I understand. What is this? Okay, yeah. So now the proof for the arithmetic progression. Sum of the arithmetic progression. So it's blue for fun. Sum of arithmetic. So I'm gonna try and prove this in 2 ways. First, I'm gonna show a derivation using our original definition of what the original definition of what our terms was, and then after that, I'm going to try and use I'm going to try and do it by induction as well. So firstly, let's think about what our original definition says. It says un is equal to a plus n minus 1 times d. And now what we're trying to do over here is we're going to try and sum up all of these until the nth term. So this is, un is this. But we're going to try and sum up u1, u1, u2, u3, all the way up until un. Now, it's extremely useful that we have this notation, because if we didn't have this notation, this would be so much harder to even think about. Let's think about what we're doing if we would sum up the first n terms. So if we write down what u1 is equal to a plus 0d. u2 is equal to a plus 1d. u3 is equal to a plus 2d. So on until un, which is equal to a plus n minus 1d. So if we were to add up, so if we were to think about adding all these up, so we put a little thing, we tried adding up all of them. And obviously on this side, we're going to get the sum of un from n is equal to 1 to n, right? This makes sense over here, what I've written over here. It's a sigma function where un, and I'm summing from n equals to 1, right over here, n equals to 1, up until n, so up until un right over here. So I'm going all the way through, I'm swiping through all the way down, and I'm going to create the sum. And what is the sum equal to? Let's try and add up all of these over here. So if we add up all the a's, how many a's are there? There's going to be n a's, because we have 1, 2, 3, 4, 5, we have n terms, and all of them have an a in them. So we know there's n a's. So we're going to call it na, n times a. But this one's a little more confusing because what exactly is happening here? So you have 1D, then 2Ds, then 3Ds, 4Ds, so on, all the way to n minus 1Ds. And you want to add all of them up. So what we're going to do is we're going to end up with a little mini sequence inside our sequence over here. So we're going to end up with a 1 plus 2 plus 3 plus whatever, all the way up until n minus 1 times d. And if anyone doesn't understand how that came about, please tell me now. Again, the deafening silence is telling me that you guys do understand. And then the most like troubling part right now is that this doesn't really help us at all. Because if we wanted a formula for the sum, we wouldn't want to have this sequence inside the sum, because we're trying to find the sequence of an arithmetic progression. But we have another arithmetic progression right over here with the starting term 1, and then you add 1, and you add 1, and you add 1 all the way up until n minus 1. That's just annoying. Like, and there's a quick way, a little trick to fix this right over here. And we're going to use this trick a little later on as well for some other proofs. But here's the trick. So we use, you know what, let's go to another color to get even more fun and spicy. Okay. So we start with some sum. And that sum is going to be 1 plus 2, all plus 3. 1 plus 2 plus 3 plus whatever, all the way up until n minus 2 plus n minus 1. I hope that makes sense what I did over there. That's the same sequence as sort over here. 1 plus 2 plus whatever, all the way up to n minus 1, 1 plus 2 plus stuff, plus n minus 2 plus n minus 1, because n minus 2 is right, less than 1, n minus 1. So I've summed up all the things up to n minus 1, and I've written it out like this. And I'm going to write it out in a different way as well. I'm going to flip it around and write it as well. I'm going to flip it around and write it as n minus 1 plus n minus 2 plus 1, no, plus 2 plus 1. So I've just flipped it around and written it the exact same thing. So these two are the exact same thing. That's why I've written them. Both are S. And this is the same thing right over here. So this is also S over here. This is what I've done over here. And now I'm going to add these two things together. So I'm going to add these two things together. And then I'm going to get 2S on this side. And that's equal to 1 plus n minus 1 is equal to n. 2 plus n minus 2 is equal to n. Skip all the ones in the middle. N minus 2 plus 2 is equal to n. N minus 1 plus 1 is equal to n. So now you have a series of n's all the way down. And how many n's are there? Well, there are n minus 1 n's, because you knew that there are n minus 1 terms. So there's 1, 2, 3, all the way up to n minus 1. If you got to count all of them, you would have n minus 1 of them. So you know that you have n minus 1s. So you have n minus 1 n's. So if you were to write this out again, it'll be 2s is equal to n times n minus 1. And this we can rewrite. As s is equal to n times n minus 1 over 2. Now, because we used that handy little trick, we've got this very complicated thing, right, in this very extended form into a closed form. So before, if you wanted to calculate the arithmetic sequence sum, we would have to, and if you wanted to do it up to the 10th term, you had to do 1 plus 2 plus 3 plus 4 plus 5 all the way up to 10. But you don't have to do that anymore. All you have to do is use this formula over here, s equal to n times n minus 1 over 2. So that's how you sum up all the things up until the n minus 1th term. So for example, even if you want to do something like 10, we know that 10, 9, 9, 8, 8. Wait a second. Nope, yeah, this is correct. This is correct. Yeah, so for 10, if you wanted to figure out 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, you would look at what n plus 1 is, what 10 plus 1 looks like, what 11 looks like, because if you would put in 11 over here, that would mean the 1 plus 2 plus 3 plus 2 all the way up to 10. So think about 11. So 11 times 11 minus 1, so that's 11 times 10, that's 110, and 110 divided by 2 is 55. So there we go, 55. That's what your solution is going to be, which is super useful. And now we can go back to our original sequence over here where we're trying to simplify. So we get NA plus n times n minus 1 over 2 times D. Now, a weird thing that the formula booklet does is that this is a closed formula. We've done it. We've basically done it. But there's some factorizing to do, some simplifying to do. And essentially the way that the data booklet does, the formula booklet does it, is they factorize out n over 2. So if you want to take away n over 2 from the a, you need to make sure that it's a 2a now. Because 2a times n over 2 is going to give you, the 2's will cancel out, you'll get na, and it'll go back to this. So 2a over here. And you add that to n minus 1 times d. So n minus 1 times d, n minus 1 times d times n over 2 is going to give you n times n minus 1 times d over 2 right over here. So that's the data booklet formula right over there. Now, this formula was obviously proven using a derivation from the original definition of an arithmetic sequence. However, you could also prove this using induction, which is done. Which is, I think I've seen it as a question in a math test, in an IB test as well. Whereas to prove this formula using induction. So what I'd like you to do is just try and do that right now. Try and prove the arithmetic sequence sum using induction, and then I'll go over how to do that right after. Okay? And I'll give you 8 minutes. I think it would be roughly 8 marks, so 8 minutes seems fair. Can someone give me some response so that I know I'm not like speaking to someone? Please.
Hello.
Yeah.
Okay, yay. Is everyone like, has everyone done it or tried it?
Yeah, I just did it.
Okay, cool. Rain?
Hmm?
Did you try it?
I tried it.
Did it work?
The way I did. Oh.
Okay, I'm gonna go ahead and explain it. It's in terms of inductive proofs, it's easier, but it's hard to spot. There's less like manipulation, but it can be difficult if it's hard to grasp the concept of induction. Let me just go ahead. Let me use red this time. It's nice. Uh, so prove by induction, what we're proving is that the sum of un from n is equal to 1 all the way up to n, which is equal to the sum of, that's a bad sig, n equal to 1 up to n of a plus n minus 1 d, which we saw above, is equal to n over 2 times 2a plus n minus 1 d. So what we're going to first try and prove is the base case. So the base case is n is equal to 1. And when n is equal to 1, let's look at what the sum looks like. So from the sum, I'm really bad at drawing sigmas if you didn't realize yet. No, that's horrible as well. What the hell? From n is equal to 1, all the way up to 1. We're going to look at what u1 looks like, what un looks like. But note this is it's just equal to a plus, it's just equal to a. Because what ends up happening is that you know that un is a plus n minus 1 times d. So if you put in a 1 inside the n over there, it becomes 0. So 0 times d, it's just a. So you know that with the base case n equal to 1, the sum is equal to a. So you need to show that this formula works for when you do the base case. So what we're going to do is we're just going to multiply, we're going to plug in n into this formula and see what it looks like. So what we're going to see 1 over 2 times 2a plus 1 minus 1 times d, right? So I took this down over here. And this, if you notice, 1 minus 1 times d is 0 times d. That cancels out. And the 1 over 2 times the 2a inside over here just gives me a. So note that this is true. So you know this is true. So you write a quick statement saying base case is true, because these two are the same thing. Because the sum is a, and our formula also works, and it's a. And now this is.
Can I ask?
Yeah.
Is it okay to use in that sigma above? You use u of n and also the index that you're adding to is also n. Is
What do you mean?
like the sequence is defined as u of n, and you're also
Oh yeah, you're
taking the
right.
sum.
Yeah, you're right. You're right. Yeah. Yeah, you're mathematically speaking, that's not very rigorous, but it's okay. It's not that big of a deal right now. It would be better if I changed it to UK and I put this as k, so the parameter in the sigma function is different from the sum. So yeah, you're right about that, but it's not that important right now. But yeah, you're right. Now for the inductive step. So I'm gonna go black for this one. So the inductive step states that if we assume that this is true for some value k, then that must mean that it's also true for every future value. So let's think about this. So now we're going to be starting to use some more sigma notation. So if we have our start with our indexes, so let's see. Let n equals to k be true. That's our first part. So we're going to let it equal to true. So what we're going to do is we're going to say that if you take the sum from k is equal to 1, no, now we're using another one. It's fine. Up until the n of uk, that's going to be equal to k from, I made this same error happens. Okay, there's too many variables. Up until k is going to be k over 2 times 2a plus k minus 1 times d. It's important that you change the variables. I think that's like a, that you don't just, this formula over here, we've written over here, don't just put n's, you have to put k's inside this formula again when you rewrite it. I know it's the exact same thing, but you need to show that you're letting it be true for some other value that isn't just n, which is anything, but it's like, but k, which is a specific anything. So you need to change the variables inside this main formula over here. So now you're assuming that this is true. So essentially what you're doing is you're assuming that the formula is true. And now you're going to try and show that n equals to k plus 1 is true. And how do you do that? So essentially what you want to show, like what the end result is going to be, is that you want to show that the sum until k plus 1 is the same thing. So what you want to show is that the sum from k is equal to 1 up until k plus 1, right? This is up to the k over here, but we're going to go up until k plus 1 of uk is equal to k plus 1 over 2. So that's, we're replacing all the k's with k plus 1s because we don't want the k plus 1. We will change the k to k plus 1. So the k is over here, we'll go to k plus 1. You have 2a, and then k plus 1, we replace the k over here, minus 1 times d. This is what you want to end up with, right? So you're trying to reach this end result. And by reaching this end result, you will show that it's that induction is true. And you're going to have to use this above formula in order to do that. So here's what I'm going to do. We're going to split up this sum over here, this sum notation over here. We're going to split it up into the sum k equals to 1, k plus 1 of uk. And we know that that's equal to k is equal to 1 up until k plus uk plus 1. Does this make sense? Oh, no, wait, I missed a term. Wait. Does that make sense? Does anyone have any objections? Can you just inform me that it all makes sense? Okay, I'm assuming it's okay. So now what I can do is I can, this uk plus 1 term over here isn't just uk plus 1. We know what it is because of our previous definitions. That is actually a plus kd. Not k minus 1d because you're adding plus 1. You're moving it up 1, so it's kd. Plus the sum up until k is equal to 1 of uk, right? But here's the cool part, and here's the inductive step. Let's see. This right over here is the same thing as this right over here. And since they're the same thing, and you assumed that this can be true, that means that this is what you can substitute into it. And this is the main concept of inductive step, because you're trying to get something over here, and because you've already seen that you could true before, you can substitute it in. That's what we're gonna do. We're gonna substitute this equation above into here. And how are we gonna do that? It's gonna is equal to k over 2 times 2a plus k minus 1 d plus a plus kd. So this all, we want to be able to take all of this and get it to here. And now it's a matter of algebraic manipulation, which albeit might be a little difficult, but at the end of the day, you know that your answer has to be correct because you know that saying, because you know this arithmetic sequence formula is true. Yeah, I know it's a little weird to use k as a variable and the incrementer is correct because I lost track of symbols and I don't want to change now. I'm just too far in. I'm too far into the horrors of what I'm doing. I hope it's not a concern. At least that the fact that you guys are able to notice it is probably good enough. So yeah. Now, if I were to put all of this, try and simplify all of this, now it's just a matter of algebraic manipulation. Doesn't matter what parameters I'm using anymore. What I can do is I can do. I'm gonna like multiply everything out again. So I'm gonna like I'm gonna multiply k over 2 times 2a and k over 2 times this over here. So I'm gonna k over 2 times 2a is gonna be equal to ak. And then I'm gonna multiply this by that. That's gonna give us k times k minus 1 over 2 times d. That's plus a plus kp. Okay. And now I'm going to simplify further. So ak plus a is equal to a times k plus 1. And then this over here and this, I can make that into a k squared minus k over 2 plus k d. Does that make sense? So I just expanded this out because I think it makes the algebra a little easier to work with. So k squared minus k over 2 plus k times d. Okay. And then I can take the k. I can actually make that a 2k over k. No, 2k over 2. So I can add these two together. And then I get k plus 1 times a plus, adding these two together, you get k squared plus k over 2 times d. However, k squared plus k, again, you can factorize that out, and you can make it k times k plus 1. So you can make it k times k plus 1. And that's, again, that's, now we've returned, now we can factorize again. So we can take out the k plus 1 and k plus 1 over 2 from both of these terms. So we factorize again to get k plus 1 over 2 in the front. And this will give you 2a when you multiply these two. And then you'll end up with a kd in the front. And you can rewrite this one more time as k plus 1 over 2 times 2a plus k plus 1 minus 1 d. And the reason I did that is because now we've got exactly what we wanted right up over here. We've got the same thing written over here as we have right over here. And that you've proven by mathematical induction. So you use the base case over here to show that, and then by letting the k case be true, now you're letting the n equals to k plus 1 case be true, and that's how you solve the induction. Now you need to have an ending statement, and the way that ending statement is done is basically saying this statement, I'm not going to write it all out, but because I'm horrible at writing, but this statement is proven by mathematical induction since base case is true, and by letting n equals to k be true, n equals to k plus 1 is also true. So yeah, that's basically the statement you have to have in the end. If you have a statement vaguely representing that, you'll get a mark. What some students like to do is that even when they haven't done the induction, like if they forgot how to do the induction, they don't know how to do the induction, they just write out the statement anyways, like without any working at all. They just write the statement out. That could get you a mark. Okay, you never know. If it's just a 4 or 5 mark induction question, that could get you a mark. That's very possible. But it's obviously better if you do the induction. But if you're really like scouring for marks, the main things that you can get marks from very easily. First of all, writing out this base case. Usually it's very easy to do the base case. You'll probably get 2 marks just from all of this over here. By letting n equals to k be true, you'll get another mark just by writing this out. By saying that we need to go up until this position, so like by saying that we need to try and prove that this can be made equal to that by doing this entire process, that'll probably get another mark. and the statement will get you another mark. So at the end of the day, you might get 3 to 4 marks with not even knowing the induction. And that's also important because now that means that you can get marks even when you don't know how to do something. So leave your induction, if you don't know how to do an induction question in a test, leave it for the end, go back to it, try and solve it, but if you're not able to do it, write out these main steps just at least write out the main steps, and hope that you can get a few marks just from that. Never waste an induction question. You'll always be able to get something out of it. So yeah, that's I've just used induction to arithmetic, some of the arithmetic progression. That's the same thing written right over here. Now I'm going to do the same thing for, I'm going to prove the geometric sequence sum, but I'm not going to use induction on it again because that'll take too long. I think it's a little more complicated in induction. Yeah, I've got a message in the chat. But yeah, I prefer proof by deduction as well. Induction, okay, the real reason induction even came out to be true, like came out as a thing, is because people were guessing, basically. So like what they would do is that they'll be like, okay, we need to prove, like, we need to, okay, say they would like think about this and be like, okay, this is what we need to prove, right? And basically what they would do is they would just say that, they would not explain how they got that or where they got that from. They'd be like, you know what, it's a pretty good guess. Like, it's probably true. And then they would go ahead and use induction to show that it's always true. Which it just like, it kind of irritates me because like, instead of trying to guess things and then prove it's true, it definitely works. Why don't you just try and prove that it's true by deduction? So this method over here is deduction, where I start off with like a main concept, and then I get to the formula. But over here, you take a guess, and then you prove that it's true. And I kind of prefer the deduction method more, right over here, the proving it, rather than just the induction of it. But of course, induction is something you need to know and something you need to learn. And just because you don't like something doesn't mean you shouldn't be knowing what it is. I think that's true for all of math. Just because you don't like math doesn't mean you shouldn't be learning it. Very useful. Here, philosophy fundamentals would think. Now let's do the geometric sequence. Geometric sequence. Let's think about what the general term of the geometric sequence is. Un is equal to AR to the power of n minus 1. And I'm going to do this by deduction. I'm not going to do this by induction. And the way I'm going to do it by deduction is by writing out the sequence and writing out the sum. So what does the sum look like? The sum, so I'm going to sum from k is equal to 1 up until n of uk, right? And I'm using the correct parameters, summing all of them up together. You start off with a, then a plus r, then a plus r squared. No, not a plus r squared, ar squared. Sorry, I'm a fool. Ar squared, all the way up until ar power n. Ar power n minus 1, sorry. Yeah, n minus 1. Plus. That's what the sequence looks like. That's what the sum looks like. And I sum all of them together. Now, I'm going to do, again, a little trickery, okay? I'm going to call this sum, the value of the sum, I'm going to call it S. So I'm going to get rid of this. I'm going to get rid of this. It's a little wordy and like a little mathematically confusing. So I'm going to call it R. I'm going to call it, not R, I'm going to call it S. Sorry, I literally said S and then wrote R. I'm going to call it S. Now what I'm going to do, I'm going to do a little trick. Note, if I multiplied everything by some number, say, if I multiply, oh, why does Ayush keep leaving and coming back? Because yeah, so what Aryan says over here, he says that induction proves an existing result and deduction gets you the result. I think both will eventually get you the result, but induction is, I actually think induction comes out, like induction seems to be the most useful thing, especially like after Euler, because Euler was on like a guessing spree. He probably like guessed like half of mathematics in like the process. So like, I think because he was kept guessing stuff, he probably needed induction. So I think that's why it's like pretty popularized. Well, obviously, because it's also induction, it's very important, but you know, it's interesting. Anyways, back to the trickery. S is equal to this. I'm gonna do a little trick. I'm gonna do RS. I'm gonna like try and figure out the value of R times S. And if I notice that's actually equal to AR plus AR squared plus all the way up to the AR n minus 1 plus a to the power of R, AR times a to the power AR times to the power of n. So what I did over here is that I multiplied all of these R's, but all these terms by R. So I got A became AR, right, like that. The AR became AR squared, like that. The AR squared became whatever, and then the AR n minus 1 became the AR n, right, that over here. And essentially I multiplied everything by R, and I got this new sequence. Now I'm going to do another little trickery. I'm going to take away the second sequence on the first one. I'm going to make it S minus RS. So now what happens is that the A over here, there's nothing here to take it away from. So I'm just going to say there's a 0 plus over here. And over here I'm going to make a plus 0 as well. So the A minus 0 is just going to be A. The AR minus the AR is just equal to is equal to 0. So AR minus AR is 0. Nothing over here. The AR squared minus the AR squared is nothing. It's 0. AR to the power negative n minus 1 is minus AR to the power n minus 1. Again, 0. So all of these terms will cancel out, except this last one over here. 0 minus AR to the power of n, you're going to get minus AR to the power of n. And that's your final little tidbit over there. Now what we can do is we can just solve for S. And the way we solve for S is like this. So first we factorize the S out on this side. We get S times 1 minus R is equal to, and we can also factorize this side. So we can make it A times 1 minus R to the power of n. And then S is equal to A times 1 minus R to the power of n over 1 minus R. Isn't that fascinating? That's very fascinating because, okay, now you can see over here, that's exactly what is right over here. And now what I think, just personally speaking, in terms of mathematics, and again, I think these like little sidetracking clues and stuff will help you with paper 3 eventually. But here's another very interesting thing, is we could have rewritten this in a different way. So let's look at that sum again, right? So we've obviously shown that this formula works now. We've deduced that. But let's look at that sum again. It's AR plus AR, it's A plus AR plus AR squared plus AR cubed, and so on, right? But there's another way we could have done this. Note that every single term is an A. So couldn't you just factorize out the A? So, well, let me just like add the n term. So I don't want to like forget that, n minus 1. So why don't we just factorize out the A? If we factorize out the A, you get 1 plus R squared plus all the way to R to the n minus 1. And this is, I find this personally very satisfying because what this shows is another property, another unrelated property. Note that S is equal to A times this stuff, but S is also equal to A times this stuff. So this stuff over here must be equal to this stuff over here. So these two things here and here must be equal to each other. Now, what does that mean? Why is that so satisfying? Look at it over here. That's what's true. Now, why is this so interesting? It's because this sequence over here is essentially just the increasing power. So you're just adding up 1 plus R squared plus R and just adding up all the powers until some value. Now you would think that that's like, this is some polynomial, right? It's some very complicated looking, like a very long polynomial, which isn't closed, right? You have to keep adding up terms up to some polynomial. So if I said like, I want to go up until like R to the power of 4, we need to write 1 plus R squared plus R cubed plus R to the power of 4 and so on. However, this all equals to something very simple like this, and very close and very neat. And I think that's very cool. I think that's very neat. And because after all our manipulation, it just shows this. And it turns out that this is extremely useful in some, yeah. Yeah, it is. Okay, so this brings out a few different properties right now. So one, this is useful because it shows the sum of a polynomial, like a geometric sequence like this. And secondly, this is a result that is that comes from long division of polynomials, which I think I'll talk about later at some point. But long division of polynomials also proves this. But anyways, this is just a very, I think, a very satisfying result from the geometric series progression. And yeah, so there, we're done with that. So I think that's everything from some arithmetic sequences and geometric sequences. Anything else that must be interesting is compound interest. But I'm not going to go over compound interest because compound interest is just the geometric sequence thing. Alternatively, it's just this formula. So as long as you know what each of the terms of this formula mean, and as long as you know exactly how this form, like this multiplication, addition, and exponentiation rules, you should be able to do compound interest questions. Anyways, it is an SL concept, so I can't wait till I'm teaching complex numbers. That's very fun. But the next thing that I'm going to look at, I think like the final thing I'm going to look at is the binomial theorem, and I will also give you an exercise to try and prove the binomial theorem using induction. But I'm going to prove the binomial theorem first of all using deduction. I'm not gonna just be a dirty old induction man all the time. So the binomial theorem, what is the binomial theorem? The binomial theorem is basically a way in order to expand binomials to some ridiculous power. So if you had a plus b, like a plus b, the power of n, what exactly is any given term of that going to look like? Yeah, only for integer powers. I'm only going to do it for integer powers. I think proving it by deduction for non-integer. Okay, so integer powers basically means that I'm only going to do for a plus b to the power 1 squared, cubed, so on. I'm not going to do halves and stuff like that. Because one, I would need to, in order to do that using induction, you need to do it, you need to use strong induction, which I don't think is in the syllabus. And then in order to do that using deduction, it'll become, you won't be able to use combinatorics anymore. So I think it's just too confusing for now, but I think I can generalize it to that, and then it should be okay to non-integers. And what I mean by non-integers is just halves and stuff, like cubes. Like if you're not doing n is not an integer. So a plus b to the power of n. What exactly does it expand into? And I'm not going to like give out the answer straight away, but obviously I know that you guys know the answer, but I'm going to go through how to do this. I'm going to do this as an example. I'm going to use it. Do it using. I'm going to do it using colors and to show the combinatorics. And this is the first time I've ever tried this. I might mess it all up, but here, we're going to try with a plus b cubed. So we're going to try a plus b. Wait, I have my colors. Yeah, okay. So a plus b times a plus b, right? So it's a plus b cubed. And we want to try and figure out all the terms out from here. Now, obviously, you can just go ahead and do all the terms out. But there's another more interesting thing that you're going to be trying to look out for, is that there's a series of different kinds of terms that can come out of this. So you can get an a cubed, obviously. If you multiply all the a's together, you'll get an a cubed. If you multiply an a times another a and then times a b, you're going to get a squared b. Or if you were going to try and do an a and then a b and then a b, you could do a b squared. And then if you want to try and do all b's, you can multiply all the b's together and then b cubed. Because when you're multiplying these binomials together, essentially what you're doing, that you can choose either of these kind of components and then multiply it by everything else, and you can choose it for each of them. So you can choose an a and b from a or a b from here, an a or a b from here, an a or a b from here. Yeah, I got a chat message. Taylor theorem. The problem with Taylor theorem is that they haven't learned Taylor series yet and Taylor theorems yet. That's the issue. But yeah, okay. I don't know if you guys can see them chat when I open it, but like, yeah. So a plus b times a plus b times a plus b. And these are all the different types of things I'm going to get. So let's think about the ways I can make this first one. So how many different ways can I make the a cubed? So I could have an a from here, right? So I can have an a from here. I can have an a from here, right over there. I can have an a from here. Oh, why did I put b? That's very stupid of me. A from here. and I can have an A from here. Now, obviously, it looks tedious, but I think it'll get the idea of combinatorics with it much better. So A times A times A, that's the way you can do it. Can you do it any other way? So this A comes from this red one, and the A from here comes the blue one, the A from here comes the orange one. But from all of these, you can only choose the A, because if you chose the B, you'll get something else. We want like only A cubed. So there's actually, it's like surprisingly, there's only one way you can do this. There's only one way you can get an A cubed. That's a weird ass color. Choose what the hell? I'll just keep it black. There's no, not red. I chose black. My God. Black. So there's one way you can have A cubes. The other thing is that how many ways can you make A squared B? So how many ways can you choose 2 A's and 1 B? So you could do it like this. You could do it with a with the a red and a blue A, and then a orange B. And you could do it with a blue and orange A, blue and orange A, and then a red B. Or you could even have a red and an orange A, red and an orange A, and then a blue B. But note now, you've actually gone into the territory of combinatorics. What you've done, what you just asked as a question is, how many ways can I choose 2 A's from these 3 different things that I have in front of me? So I have 3 different binomials. I need to find a way to choose 2 A's from them. And I can choose any 2 combinations of A's, but I need to find a way to choose it. So what I'm doing here is I'm doing 3, choose 2. So what I'm doing is 3, choose 2. So if I would look at this in terms of here, I'm doing 3, choose, not 3, choose 2. I'm doing 3, choose 2, which comes from combinatorics. So 3, choose 2. And note that in the first one, what I was doing was that I needed to find 3 A's from these 3 binomials. So essentially what I was doing is I was doing 3, choose 3, which happens to have a value of 1. So I'm doing 3, choose 3. And now for AB squared, I'm doing the exact same thing, but I'm changing it a little bit. What I'm doing now is that I'm only choosing 1A. So how many different ways can you choose 1A from each of these different ones? So then that's a 3, choose 1. How many different ways can I choose A from this series of different things? And then over here, I can choose how many different ways can I get all B's? How many different ways can I choose 3 B's from these 3 binomials? And I end up getting 3, choose 3. And note now, note how this value is changing over here. The top value is always n. This always happens to be n. So this was equal to A plus B cubed, right? And our n value is equal to 3 because that's what you're cubing it. That's what we're taking to the power of. So n, the top value is always n, right? In a term like this. However, the bottom value is the same as the value of the A over here. Right, like that, which is the one there. And then over here, technically I should not have put 3. I could have put 3, 0, because the A's, how many ways can I choose no A's? There's only one way I can choose no A's. And then again, that corresponds to some imaginary A to the 0 over here. And this is how I've just like shown a large part of the binomial theorem. And then the way that we can check the general term of a binomial theorem usually is by doing this. We do n choose k of a to the power of n minus k, b to the k, like that. And essentially this comes from here. And it comes from the idea of trying to figure out all the possible ways you can make something. And for cubed, you did this, but now you can prove that this works for, so for any given term is going to look something like this. I mean, this is not equal to this, but this is just one of the terms. So one of the terms. And this comes up in your data booklet. So this comes up in your data booklet right over here. Sorry. Here, so under your binomial theorem right over here, you have a plus b to the power n is equal to a to the n plus nc1, an minus 1 times b. And then over here is the general term I just came up with right over here. It's written right over here. They use the C notation, NCR, so N choose R. I use the bracket notation. You can use either one. There's no issues with either one. Just make sure that you're able to know how to, what the NCR means. So using this right over here, you'll be able to do it. Now, obviously this leads us to another little trick that we know from math is the Pascal's triangle. So we know that the coefficients from the binomial theorem can also be derived from Pascal's triangle by doing by writing out as rows of ones and basically trying to find out using the numbers from here in order to actually find out what the what the coefficients are for each term. But we also found that we can also do it using this methodology, which is using the choose. And the choose method with combinatorics is what the formula uses. But you can also use this method. However, the issue using this method is that you can get a very large Pascal's triangle. And you don't want to get a very large Pascal's triangle because then you can mess up numbers and values. So it's much more advised to use this choose method always, almost always. But if you have something really small like a plus b cubed, you just want to, like, you forgot what the numbers are, you quickly want to check, draw this out really quickly. You can figure out it's 1, 3, 3, 1. And indeed over here, you know that 3 choose 3 is 1, 3 choose 2 is 3, 3 choose 1 is 3, and 3 choose 0 is also 1. So you know it's 1, 3, 3, 1. But basically, you just use this for quick and very small numbers. Maximum to the power of 4. Don't do anything more than to the power of 4. You will get too confused. It will get too confusing. Just use the chooses always. And the good thing with this choose methodology is that you can arbitrarily select any term from the middle. You don't have to like use some big brain like thinking to try and figure out where everything is. But here's how you do it. This is your combinatorics way. Now it's very important that you understand why this combinatorics thing works, not just because it's important to know why the binomial theorem combinatorics works, but also why why new theorems might work this way. Because understanding why this works and how this works can help build your mathematical inventory of proving tools. So while induction is a very good tool of proving, deduction is often very necessary. So you need to be able to bring in different fields of math, such as probability and combinations, and also algebra, in order to come up with a final solution. Because in your paper 3, that's exactly what they're going to try and lead you to do. And if throughout the 2 years of your learning of your course, you're not practicing these skills, by the time you read paper 3, you will not be able to do that. It's almost like a language. You're not going to be able to study something just a week or a month or 2 months before a new language exam, because you can't learn something like that. You need to learn languages over a long period of time. And in this case, math is sort of treated like a language. And math is a language, of course, but sometimes you can like rush and study for it. But in this scenario, the IB isn't going to support you during the test. They aren't going to give you all the answers. They're going to leave it to you, and they're going to ask you to try and prove it. So something like this is fair game in the test. They would give you some more hints along the way, such as like how many different ways of this, how many different ways of this, and you might need to start thinking about combinations. But then it's going to be slightly more difficult than how previous curriculums are, and how past papers look, and how paper 1 and paper 2 look. So yeah, that's just what I want to emphasize on. And if you really want to try, you can always try proving this by induction as well for all integers. That's also possible. You can try and do that. It's not a particularly difficult induction to try and show, but it would be it'd be cool to try that. And you can try and do that. And you can do that, and if you do it or you need help with it, you can also DM me and I can explain how it works later. But yeah, that's the end of the session. I think I've gone over everything I need to go over today. I'll check when I'll schedule the next session. I'm not sure. But yeah, that's all.
Lake, I just have one final question.
Yeah.
Does this count for your CAS?
Yeah, it does.
Okay, thanks. Because I think I'll do this for my school too, next year or the year after that.
Yeah, it's really good CAS because it's like online. So it's good for the like during the epidemic. So yeah. Yeah, that's the real questions. CAS. I think anyone good at math should be doing this for CAS. It's not. There's a lot of people trying to like get math help, especially considering it's the new curriculum is like AA and it's kind of confusing. Anyone who is good at math should definitely be doing this. It's very easy CAS. Just explaining, and that can go a long way. So yeah. Anyways, yeah, it's a CAS project. Actually, what I did was I combined like the revision sessions. So I did the November revision sessions, the May 2020 revision sessions, and these, and they're all in one big thing. And like I have like some 100 pieces of evidence in like one big folder. It's ridiculous. Anyways, I'm done. I'll